Okay, this is part 4 of the screencast on cosmology. Let me go ahead and finish my description here of this diagram. Once again, this diagram is referred to as broken symmetry, and it describes the events that occurred very early in the history of the universe. From 10 to the minus 43 seconds going all the way forward to today, we have a pretty good understanding as to what happened. So between 10 to the minus 43 seconds and 10 to the minus 35 seconds, we have this inflationary epoch, as it's called. This is where the size of the universe increased by 26 orders of magnitude, and the forces begin to split off from there. Okay, at a period of time of 10 to the minus 12 seconds after the Big Bang, that's, by the way, only a trillionth of a second after the Big Bang. The temperature of the universe at that time was about 10 to the 14 Kelvin, and this is the point in time where the electroweak force begins to split off into the weak nuclear force and the force of electromagnetism. At just a millionth of a second after the Big Bang, this is when what is called baryonic matter forms. The temperature of the universe at this point is cool enough for the individual quarks and leptons and so on and so forth of the Standard Model to begin to combine together into protons and neutrons. Protons and neutrons collectively are referred to as baryonic matter. And then about a minute or so after the Big Bang, that's when the temperature of the universe was about 100,000 degrees Kelvin. It's at this point where protons and neutrons can start to fuse together with the process of nuclear fusion. This process of nuclear fusion that occurred in the entire universe at this period of time is referred to as BBNS, Big Bang nucleosynthesis. This period of time didn't last all that long, but while this period of time was going on, nuclear fusion was occurring in the universe. If you work out the mathematics of the theory behind Big Bang nucleosynthesis, it predicts that the elements should have the following proportions. 76% of the universe at this point should be hydrogen, and about 24% of the universe should be helium. Now, when we look out into the universe today, and we look at individual galaxies, for example, this is exactly what we see. Galaxies basically are 76% hydrogen, 24% helium, a little bit less than that, and just a small scattering of basically everything else on the periodic table that is formed from nuclear fusion processes that occur within the core of stars. Besides the relic radiation of the Big Bang itself, the cosmic microwave background, another pillar of evidence, if you will, that we have for all of this is the proportion of the light elements that exist in nature. Big Bang nucleosynthesis predicts that the universe should be 76% hydrogen and about 24% helium, and that's exactly what it is when we look out into the universe. And then from a time of about a minute or so after the Big Bang itself to a time of about 380,000 years after the Big Bang, the universe cools down from this point to a temperature of about 1,000 degrees Kelvin. It's at this point right here where neutral hydrogen atoms form. Not the nuclei, which formed earlier, but this is where a proton, for example, comes together with an electron to form a hydrogen atom. Neutral hydrogen atoms form at this moment in time. It's kind of like a fog, if you will, clearing in the universe, and this is when the universe becomes transparent. Therefore, the cosmic microwave background dates back to this moment in time. Okay, let me go ahead and go back to the main slideshow at this point, like so. Let me start to skip ahead a little bit here on my slides. Specifically, let me go to this slide here. Okay, as I mentioned very early on in this screencast, everything that we've seen in the study of the nature of the universe from essentially the publication of Principia in 1687 forwards has been pointing in a specific direction. Our understanding of the laws of nature are coming together to ultimately describe perhaps a final theory of nature. That final theory of nature, once again, is just right now generically referred to as quantum gravity. This is basically what physics is looking for today. Right now, our best guess at quantum gravity is string theory. All right, this is just a really nice artistic depiction of my space-time diagram that I drew on the board for you earlier in this screencast. Space-time diagrams that describe the entire history of the universe itself lend themselves to very colorful descriptions and so on and so forth. All the details that you see here on this nice colorful diagram, this is what I drew out and explained earlier in the screencast. Maybe one day I'll eventually tattoo this somewhere in my body. Okay, now getting to galaxy formation. Remember earlier on my space-time diagram, I described the Dark Ages. The Dark Ages is a period of the history of the universe after the formation of the cosmic microwave background, but it's basically a period of time where the first stars form, the first galaxies begin to collect from those stars, the seeds of the first supermassive black holes form, and so on. This region of the universe is not very well understood. Our best bet, however, for galaxy formation to occur is as follows. We think that it follows what is called a bottom-up structure formation, where you have small individual clumps of collections of stars, which then gather together through galaxy collisions to form the big mature spiral galaxies, for example, like the Milky Way that we see today. Okay, earlier in my screencast, I also mentioned this project of the Hubble Space Telescope called the Hubble Space Telescope Ultra Deep Field, and I described it on my space-time diagram. Once again, what they did with this project was they took the Hubble Space Telescope, pointed it at a rather insignificant point in the sky, and then basically continuously exposed the telescope to the light over this period of several weeks. What you're looking at here is basically a slice of the universe going back to the early history of the universe, maybe about 400 million years or so after the Big Bang itself. Think of this as being analogous to like looking at geological layers in rock formations. The further down that you look in geological formations, the further back in time you're looking. It's like we're looking at individual layers here as we peer back in time. So relatively close to us in the relatively nearby past, if you will, we see, for example, say here and here, relatively ordinary looking spiral galaxies. But when you look much further back into the time of the detail of this photograph, this is where we see objects that look like this. Basically, we don't see any galaxies today that look like these clumps here, where you have a huge amount of star formation taking place in a relatively small volume. And then the bottom-up theory goes that these fragments then collide and collect together to produce the larger galaxies that we observe today. Okay, now this right here is depicting the large-scale structure of the universe itself. The large-scale structure of the universe is as follows. Galaxies are not actually kind of just scattered randomly throughout the universe. They are clumped together in superclusters, and these superclusters gather together along these extremely large and long filaments. So when you look at these individual dots right here, for example, you're looking at galaxy clusters. And then surrounding the galaxy clusters, well, I guess I should say the galaxy clusters themselves are surrounding these huge voids in space where there are no galaxies at all. We believe that this structure, the large-scale structure of the universe, formed because of the minute differences in temperature in the cosmic microwave background. As I briefly mentioned earlier in one of the screencasts, I said that we believe that the cold spots, if you will, in the microwave background is basically portions of the universe where the galaxies were able to come together and form. That is, form superclusters of galaxies that would correspond to these filaments. And then the hotter portions, if you will, of the microwave background, that's basically where the temperature was a little bit too warm for matter to clump together, and that then resulted in these huge voids where you see no galaxies whatsoever. Now this right here is a picture from a supercomputer simulation that mathematically describes all of this, but this is what we actually see when we look out into the universe. And when we look out into the universe, we see this in every direction. That's what's being described here in this map. So this map is a description of the following. Right here is the location of the Earth, and then what we're doing is we're looking out in one direction of the sky over a distance here of a couple of billion light years. And we do this in one direction like so, and then 180 degrees away in another direction like so. And then we look over right here at a specific angle in the sky. And then each individual blue dot that you see here is a mapped out galaxy, how far away that galaxy is from us, in this case in terms of billions of light years. And the universe basically looks the same in every direction. Once again, these two slices here are 180 degrees apart from one another. And then as you can see here with these maps, in fact of what we saw in the previous simulation map like so, this is exactly what we see. We see galaxies clumped together in superclusters. The superclusters then trace out these huge filaments, and then these huge filaments then are basically surrounding these huge voids where there are no galaxies whatsoever. So this is describing the large-scale structure of the universe as a whole. Okay, and then lastly, what might be the future of the universe going forwards as it continues to expand and cool? Well, there are a couple of possibilities. One possibility is called the heat death of the universe. The heat death of the universe is essentially what happens when entropy wins the game. Entropy, a description of the second law of thermodynamics, basically describes how, over time, matter and energy get increasingly disorganized. In other words, right now, the universe is extremely ordered. It's ordered into planets, galaxies, and so on and so forth, where the energy is essentially concentrated in very specific places. However, over time, as energy transforms from one form to another, some of that energy is always lost as random heat. If you give the universe enough time, eventually entropy will win the game. Approximately 10 to the 100 years from now, a Google years from now, there will actually no longer be any physical processes. By the time you get to that point in time, there will be no galaxies, there will be no stars. Ordinary baryonic matter will actually break down over time, and the supermassive black holes that we see today will completely evaporate. Now, 10 to the 100 years into the future, that's an enormous amount of time, and it's extremely difficult to wrap your head around exactly how much time that is. To give you an idea, right now the universe is about 14 billion years old. Okay, 14 billion years old is roughly 10 to the 10th years old. Now, 10 to the 11th years old is 10 times greater than that. 10 to the 12th years old is 100 times greater than that. Go all the way up, for example, to 10 to the 99 years in the future. 10 to the 100 is 10 times greater than that. So these numbers here are extremely difficult to comprehend. They are extremely difficult to wrap your head around exactly how much time this is. But if you do give the universe enough time, this is one possible fate. Another possibility, however, is sometimes referred to as the Big Rip. A more complete understanding of dark energy is necessary for us to understand this further. But remember what I said earlier about the accelerating expansion of the universe. The accelerating expansion of the universe is right now only measurable over billions of light years. However, as the universe continues to expand and accelerate, then that accelerating expansion will soon be able to be measured across millions of light years, and then maybe thousands of light years, and then maybe tens of light years, and then maybe within, for example, the size of the solar system itself. And then therefore the solar system would start to get ripped apart by the accelerating expansion of the universe. Maybe it will eventually get to a point where the accelerating expansion will be so large that it'll be down to the scale of planets, and planets will get ripped apart. And then perhaps down to the scale of molecules. Molecules get ripped apart by the expanding universe, atoms get ripped apart by the expanding universe, and so on and so on. So this possibility is referred to as the Big Rip. We are not sure which of the two scenarios is more likely, the heat death or the Big Rip. A more complete understanding of dark energy is necessary to explore the eventual fate of the universe. Okay, lots to ponder here as well. I'll go ahead and conclude this screencast here covering cosmology.